Thank you.
Thanks very much, Namir. Thanks all for coming out, and you know, the popularity of this talk is the evidence is in the room that we had to move rooms to accommodate everyone. I know you will not be disappointed. So Professor Moehle has many claims, and I've told him I'd keep it short because we all want to hear him talk, not me. But he's a member of the National Academy of Engineering in the US. Probably one of the most significant things is that he is the outgoing chair of ACI 318, the concrete building code in the US, for the past 5 years, with significant changes happening in the design of concrete buildings during his chairmanship. I grew to know Jack as his student, one of his first students when he was director of PEER, the Pacific Earthquake Engineering Research Center. And one of the aspects that I really took from Jack was his desire to teach his students and to encourage his students to go forward with their own ideas. And Jack has continued to support his students long after the time in school. So I appreciate that, and I appreciate that Jack has come all this way to teach us about all of the work that's been done under PEER and beyond with the performance-based seismic design of tall buildings. Jack Moehle.
I got this. Thank you so much, Ken. It's really my pleasure to be here, and it's really an honor to see this large group in attendance. And I hope you'll find the discussion interesting. And I'm really glad that it was a big group because we got to move to the chemistry building. And I've never given a lecture in the chemistry building before in front of the periodic table of the elements. And I want to point out number 97 up there, berkelium, which has something to do with Berkeley, I think. So anyway, tonight I want to talk about performance-based seismic design or earthquake-resistant design of tall buildings. And what I really want to focus on is how are we designing the buildings in San Francisco and Los Angeles, San Diego, Seattle, and so forth. From a first-hand perspective, being involved with many of the projects there. I'm sure, and I know there's many tall buildings going up in Auckland, impressive ones. And I'd love to hear how the designs are going there, but I don't know, so I can't speak to those. This photograph here is one of the pictures of the skyline of San Francisco. And that skyline has really changed in the last decade because of the large number of very tall buildings that has gone up. You can't even imagine from what's shown here what has happened, but one of the most iconic buildings now is this one in the center that towers above all the other adjacent buildings. And there's a few other buildings that are catching up, but I think it'll remain the tallest building in San Francisco for some time to come. And a little bit of what I'll talk about will focus directly on the design for that building, because I think it's interesting. The change of the skyline in San Francisco has caught the attention of lots of people, the local newspapers, the national newspapers. Even the New York Times has had a couple articles about the tall building surge in San Francisco. One of them entitled San Francisco's Big Gamble. And it's interesting, when you find that earthquake engineering and structural engineering is in the headlines. I'm not sure that San Francisco's Big Gamble was the headline I was hoping for. But I don't think it's such a big gamble, and I hope we'll see as we go forward a little bit with some of the presentation that things are being done in a fairly logical way. To start out, though, I wanted to plot up the growth of tall buildings in California. So this is a plot showing the highest building in California in meters as a function of the year. So each building is shown by a circle. And if there's a circle, it means it became temporarily the tallest building in California for that period. And we start out with the Chronicle building over here from about 1890. That building survived the San Francisco earthquake. It's become the facade of another taller building now. So it still exists in some form. The next building shown across is the Standard Oil building, still in operation today in San Francisco. LA City Hall is the third building. Has anyone ever seen that building before? I first saw this building growing up in the Midwest watching television. It's the building that Superman could leap over in one single bound. So a very famous building for that purpose and others. The Transamerica Tower, an iconic building in San Francisco. When first constructed, it was not so favorably seen by many of the San Franciscans. It was kind of an oddball-looking building. But they came to love it over the years. The next thing in Los Angeles is the U.S. Bank Tower. I only know that building because I was deposed in there once related to some earthquake damage. And I'll never forget. And then the two buildings that are at the far right, Wilshire Grand in Los Angeles and the Transbay Tower or Salesforce Tower in San Francisco. And the one on the left is claimed to be the tallest building on the West Coast, but only because it has this spire that reaches way, way up into the sky. And the Salesforce Tower in San Francisco is really taller. So don't let the statistics fool you there. Now, today we have tremendous power in computing, tremendous knowledge in the response of structural components that helps us design our buildings. We'll show some of that. If you go back, though, into like the 1930s and so forth, the designs were really based on very, very simple hand calculation kinds of methods. And I wanted to bring out an old book that sits in my shelves at home by Hardy Cross on continuous frames of reinforced concrete. And that's Professor Cross from the University of Illinois. And he devised this method known as moment distribution. How many of you have been taught the moment distribution method? Quite a few. I'm not sure whether in the classes today the young students are getting that method. It's a very powerful tool, very powerful way of thinking. You know, the idea and figure at the top, you've got a beam that's statically indeterminate. You fix some degrees of freedom, apply the load, calculate some fixed end moments. There's an unbalanced set of moments here. You apply those as an unbalanced, or as to balance the moment, you apply that in the next step. You use the principle of linear superposition to add the solutions together, and you get the answer. And this became, and was for 30, 40 years, the most powerful analysis tool that we had at hand. So Hardy Cross really had a lot to do with being able to analyze buildings back in the 30s. He also had some other funny things that he wrote. This is another book that collects some of his writings from the 1950s, and the writings go back into the 40s. He wrote about standardization. And what he wrote is peculiar. It says, as the size and complexity of projects increased, it became desirable and even necessary to set up a series of routine procedures for analysis and design. Good? With these standardized formulas and specifications and methods, it became possible to use a greater number of men, women, and men with less training to produce engineering work. Bear in mind, this was written in the 1940s, and by and large, it was men at the time, and it's great to see that changing. And then his last sentence is very odd. Standardization as a check on fools and rascals, or set up as an intellectual assembly line, has served well in the engineering world. Think about that one for a moment. it really doesn't portray us very well in structural engineering, does it? First, there's the fools and the rascals, which is fun to quote. But the notion of an intellectual assembly line where engineers with less training can produce engineering works efficiently and safely, it doesn't sound right. But this was the thinking at the time. And standardization in our codes has helped us achieve this. Build safe buildings safely without the highest levels of training that might be possible. Now, that works really well, of course, because it gets applied mainly to the majority of buildings that we construct. And in the United States, the majority of those buildings are buildings 1 to 3 stories, 93%, according to this tally. If we go 4 to 13 stories, we pick up the next 6%. The last 1%, the ones that we find really sexy and appealing, it's a very small segment of what we build. And of course, the standardized codes really aren't written for those buildings. You can't have an assembly line of engineers who are not so well trained designing them by reading a book. It takes something more. And that something more is where I'd like to focus my talk tonight. But don't forget Hardy Cross, a very interesting fellow. We can tell stories about him all night long if we wanted to. These tall buildings have different dynamic behaviors than short buildings. This is a model of a 42-story building. Watch what happens. This is the displacement. These are the story shears. It reminds me of my grandfather's handheld drill, which is not a good image. But look at how the shear forces wiggle back and forth. This structure is driven in shear forces by the second mode response, second translational mode of response. And a standardized code procedure is not going to understand how that works really well, and it's not going to do a wonderful job in setting the design requirements. What's going on down right at this level here? Well, that's the transfer level, where the tower comes down and enters into subterranean levels, and that's where the reaction forces, the joint of the building, so to speak, is. And so you get those big reverse shears. So you need different procedures for the design of these kinds of buildings. These kinds of buildings are also specialized in that the framing systems are different from what the building code prescribes, at least in the United States. In the United States, if you're going to build a tall building over 150, 180 feet, how many meters is that? 60 meters. If you're going to design a building over that height and it's going to have a concrete wall for seismic resistance, it must also have a frame to go with it. Now, the frame is there kind of as a backup system to provide a little bit more redundancy, a little bit more confidence that the system's going to work. But engineers began to challenge whether that extra frame is really necessary, especially if you're doing a good analysis and good design and good detailing. And also that frame got in the way of the occupants of residential buildings having wonderful views of San Francisco. And you do get wonderful views of this city from these buildings. And so they began to explore the idea of taking away some of the framing and putting up structural systems that aren't in or are not permitted by the current building codes. And so that's another reason why you need some specialized procedures. Going back to about, I guess about 13, 14 years ago or so, in San Francisco was the start of designing these kinds of buildings completely outside of the code prescription. And for a while, it was the wild, wild west. If you're familiar with the cowboy shows from the 60s and 70s, as I am. Engineers on one side of the street were doing something completely opposite of what the engineers were doing on the other side of the street. And one review panel would say, you're not allowed to do this. And the other panel, for almost an identical building, would say, you must do this. And it was confusing and difficult for the engineers and for the city to review these things. And so we set out to organize practicing engineers and researchers to come up with some guidance and some consensus on how to design these buildings. So the Tall Buildings Initiative was started. Some guidelines were written to get us at least some organization, some usual design methods in place that would be repeated over and over again. And the engineer didn't feel as if he or she was sticking him or herself way, way out off the limb of the branch, so to speak. More recently, the ACI Building Code, ACI 318-19, is just going through the final stages of being completed, should be out in June of this year. It has an appendix that has the title Design Verification Using Nonlinear Response History Analysis. So this is a set of building code provisions for reinforced concrete construction put together by the ACI Building Code, the 40 members of that committee, to be compatible with this document. So that, in a sense, the experts in reinforced concrete are taking ownership of this procedure so that standardized methods going forward for concrete will be in the concrete code. And the American Institute of Steel Construction is working on a companion document for steel buildings. Okay, so that's the direction the U.S. is headed currently. These alternative design methods up till now have been permitted by some clauses in our building codes. And you can read the purpose statement. Why did we go about developing these guidelines and so forth? Well, it's to enable the design of tall buildings by alternative methods and design, it doesn't say so, but by design, I think, in a better way than the Hardy Cross code methods would permit. But your idea from the building code is that the building official shall permit the design of buildings that use alternative methods or materials or ways of designing if it's demonstrated that the structural design as developed is not less in performance than buildings designed by the provisions of the code. So that's the escape clause that's allowed the design of these buildings to move forward. And it's important to note, it doesn't say that are better than performance of buildings designed by this code. It says not less than. And by and large, the design of these taller buildings is targeted at a performance level that's not less than the minimum permitted by the building code. It's not something special, usually. The risk categories, as we define them in the U.S. codes, we get risk category 1. These are like barns. This is where your sheep live. So that doesn't require such important design. Buildings, number 3, if you've got very large economic impact or many occupants, might be a risk category 3. 4 is an essential facility. Most of the tall buildings are residential or they're office buildings that aren't so big. They fall into risk category 2. And that's what most of the owners are targeting. One can, however, with these design procedures, determine that your building is important because there's a lot of people living in it, or the building's iconic, or the building threatens the surrounding neighborhood because it's so tall. And so it's possible to up the risk category and design for something better, but it's pretty rare. And that's not my decision. That's just the way it is in the design practice, in the building practice. When we design by Hardy Cross's prescriptive methods, we always design for what we call the design earthquake in California. And so the design earthquake is 2/3, more or less, of something we call a maximum considered earthquake. And we design at that level, and that should provide enough strength that the building will be serviceable under some undefined earthquake, and it should have some reserve against collapse in some big earthquake. But even though that's been the intent, we've never designed buildings for that until very recently. And what we're usually doing today is we're setting aside the design earthquake completely, and we're designing the structure to be stable under MCE level of shaking and to be serviceable under some shaking that's got a 50% probability of exceedance in 30 years. And that 50% probability of exceedance in 30 years is defined by a response spectrum at not 5% damping, but 2.5% or less, depending on the building height, because these tall buildings tend to have lower effective damping and energy dissipation. Some designers still start the design process by looking at the design earthquake. They're used to doing it. It gives them some proportions that they can lay out the shear walls and the other framing and get started, and then they set the results aside. Some cities, like San Francisco, do require that the engineer actually do the design earthquake check, but they can change the R factors. So de facto, they're saying, yeah, do the design check, but you don't have to follow all the rules that are in the code. So it's a nominal check in most cases. In terms of seismic hazard analysis, I'm no expert at it, so I'm not going to spend much time, but it's worthwhile seeing what we do in terms of selecting ground motions and so forth. Here on the right is an elevation of that Salesforce Tower next to the Transbay Transit Center. All of these things have been in the news lately. And there's UC Berkeley, by the way. For any students who are interested, that's where UC Berkeley is. We have a very exciting location. The Hayward Fault goes through our football stadium, and we're waiting, and it slips gradually with time, and so we get to see how much it moves every year. But we're waiting. It's overdue. Across the bay, the San Andreas Fault is there, the very famous one. And this building is located about there. Okay, so it's a very active environment, a very complicated environment. And engineering seismologists are always brought in to do a site-specific hazard analysis to assess what is the hazard level at this site. And generally it gets put together in terms of uniform hazard spectrum. And uniform hazard spectrum means that the hazard or the risk is uniform at every period around the length of the range of the period zones. And so this is the same probability of exceedance there at that period as it is way over there. Now, no one earthquake can cause all the spectral ordnance to be that high. This is made up of the contributions of many different rare shaking events. And what's become very common in the design of these buildings is to identify predominant vibration periods for the structural system. You hope that you can find some predominant first mode periods and some second or third modes where all the periods kind of line up. And then to define what's referred to as conditional mean spectra. And the essence of this is if you are at period 1, you would like your response spectral ordinates that you're going to design for to be at the peak for this hazard level. But if you have a ground motion that gives you that peak, as you move to shorter periods or longer periods, the probability of also being way up at the uniform hazard levels is small. And so what's done is to define what's the expected spectral ordinates as you move away. And you can see the blue curve dropping off here. By the way, that's a log-log plot, as seismologists like to use. So it drops way off. And the expectation is that by doing this, there may be some economy in the structural design. I'm not convinced that that's the case. We're doing some research now looking into this. If you have a response that's dominated by period T2, then what's going on at T1 doesn't really matter. So the fact that you have reduced the ordinates related to that with this green curve here may not really help you so much. But sometimes it helps a little. Mainly what I think it's doing is it's helping to keep the engineering seismologists employed because they have twice as many ground motions to select now with that. In any case, we do not permit the response spectral ordinates to drop anywhere below 75% of what the uniform hazard spectrum is. So we make sure that this game playing doesn't result in ordinates that are too low. The engineering seismologist knows what parts of the seismic environment contributed the most to that seismic hazard. So here we're looking at 43-year return period service level. and 2475 maybe MCE. And you can find there's different distances and magnitudes that contribute most to the hazard at those different return periods, and at this spectral period of 4 seconds. And so that helps the engineering seismologist to pick out ground motion records to use to test the building. So that's a fundamental piece of information that comes out of this. I hope no one can read this slide. It's intentionally too busy. But in essence, what's being done today is to go into the next generation attenuation relation ground motion database and to pull out from that database all the records that might be relevant for testing this building. And so you can see maybe in the broken line in red, there might be a series of records that represent the local event at a certain distance. And maybe there's a few records in the upper right that represent the huge earthquake at a greater distance. And so then the next thing to do is to narrow down which of the earthquakes require large scaling. And if you require a scaling factor that's too big, you throw those out. Which ones have the right duration associated with them. You can't use earthquake ground motion records that are 4 seconds long to test a building that's got a vibration period of 8 seconds. And so we look also at what records have the right frequency content in terms of impulsive motions. So if you're near an active fault, there's a certain percentage of motions you'd expect to have an impulse, and you would expect that to be distributed around your target period and so forth. And that's as much as I know. This is an engineering seismology field. But records are selected, they're scaled, the frequency content might be adjusted such that the scaled record fits a little bit better. These days, it's unusual to match the ground motion spectrum exactly to the target, but to have a rougher match associated with it. And typical sets of motions look something like this. So we start out with an acceleration history, and then it gets scaled, and then there's the frequency content is adjusted, and so we look at the acceleration histories, the velocity histories, the displacement histories, how the energy builds up for Arius intensity. We pull out what the velocity pulses look like, so we make sure that when the record is scaled and adjusted, we're not turning it into something unnatural. And I always read these reports and enjoy reading them, and I don't really know what to make of them. But I learn a little bit more each time. But there's a great deal of care taken to select a set of motions that's representative and realistic. We only look at horizontal pairs of ground motions. We don't ever use vertical motion. Why not? No one's demonstrated its importance yet. We're working on studying that. And we tend to use just 11 earthquake ground motions at any one period that we're looking at. So if we have a 2 conditional response spectra, we would have 22 pairs of earthquake ground motions that we use for the test. Why 22? It's 2 times 11. Why 11? Well, you get a certain probability that you're going to be within 20% of your expected result when you use those records. Okay, the bigger the sample, the more likely you're going to get something close to the mean. All right, the buildings are of several types, but most of the buildings going up have a core, a reinforced concrete core, and some of them have steel framing for gravity framing around them. Most of them have unbonded, post-tensioned, cast-in-place floors that are used for the gravity framing. And I bring this to your attention. We don't have any hollow core, Charles. And we usually have reinforced concrete framing. And even though we normally wouldn't include that as part of our seismic resistance, when we use these procedures, we model the resistance of all the parts of the building, including the gravity framing. So the typical structural model ends up looking something like on the left. The core wall is typically put together with fiber elements. We generally would have the slab to column framing represented with some approximations with some outrigger beam column elements. At the diaphragms, the transfer level diaphragms where the core and the tower goes into the basement, there's a tremendous force transfer. And how that force transfers out or in the building depends tremendously on how you model the stiffness. And so that stiffness is very carefully modeled. We don't know how to model it, so we have bounding analyses that are required. You have to use twice what you think the stiffness might be and maybe half of what you think it might be, and take the worst answer. And then the elements that are expected to respond nonlinearly in most of these buildings, concrete coupling beams or composite coupling beams, the nonlinear model represents strength and stiffness degradation directly. And so that's part of the entire procedure. And these things are pretty well calibrated to lab tests. We hope what goes on in the building is like what's in the laboratory. We're waiting for our earthquake to tell us. And I guess that is San Francisco's big gamble. At levels where the tower changes into more of a podium structure, there are force transfers. Those levels have to be modeled in terms of their flexibility, and they have to be explored. And levels above and below that have to be modeled also, because how the forces transfer in and out depends on the local modeling. If we have different kinds of walls, like this tower wall on a mat and a blade wall on a spread footing, then we model the soil foundation structure flexibility so we can tell how the forces transfer. Otherwise, a rigid base model is the norm. The acceptance criteria. They go on for pages, of course, in the document, but it's boring to read those things. But to illustrate, we look at, for this service level shaking, usually it's done with a linear elastic model, modal response spectrum analysis. We check that story drift ratios are not more than 0.005. Looks like total drift. We're talking story drift, though. We make sure that coupling beams and wall elements that might yield in the maximum considered earthquake shaking, make sure that they stay effectively in the linear elastic range. A little bit of overstress is permitted if it's a ductile element. That's the essence of the service level check. When we get to MCE, this is the slide that could take the rest of the period, but we'll try not to do it. We select earthquake ground motions to represent the hazard. We build the nonlinear model. The mean of the transient story drifts that you get out of their 11 ground motions is not to exceed 3%. The residual story drift is supposed to be less than 1%. And we don't want these tall buildings to be leaning in such a way that a city would close down the adjacent neighborhoods. Deformation-controlled elements are generally allowed to rotate as far as the computer software will let them go, as long as the building stays stable. Many engineers restrict the rotations, though, to be about 6%, such that it's pretty assured that you're not losing strength through cyclic loading in the element. Strains are modeled. I don't believe the strain value is calculated, but fortunately, they're all really small. And that's a good thing. And then when we calculate things like shear in a shear wall, we call that it's a behavior for which we don't want inelastic response. So we call it force controlled. And those kinds of elements have to satisfy this load combination. So there's a dead load effect. So we've got dead plus some make-believe vertical component. You've got live load. You have your transient earthquake shear minus any shear that was associated with gravity load, but for a shear wall, it's 0, times 1.3. The 1.3 is intended to give us that 10% risk of damage that might lead to collapse. That's in the risk category for category 2 building. And if you get into a category 3, then this I sub E factor kicks in and you have to go more standard deviations above the mean. That has to be less than a strength reduction factor, which comes out of the ACI building code, a nominal strength, which comes out of our ACI building code, and then a factor that's been made up to reflect the fact that for some kinds of behaviors, the building code is conservative in representing what the strength is. And here's an example, wall shear strength. We know that the shear strength degrades and drops down to some lower value as the ductility demand goes up. It's typical of many kinds of concrete elements. Most of these core wall buildings have very, very low ductility demands. So it's permissible to take that overstrength into account through that B factor when you're doing the design. And it's routinely done these days. And that's now been adopted into the ACI building code Appendix A without touching it. I was surprised. There are other things that you could check, but that we don't normally require as part of the design. You could check non-structural components using the accelerations that you get from your nonlinear analysis. Most engineers just use the building code requirements for tying things down. You could worry about your neighbors. For example, this tall building is sitting right next to the Bay Bridge. You could spit from the 4th or 5th floor and hit the bridge. It's really close. And so, we want to be sure, and we include in the guidelines that the cladding doesn't come off, right? You want your cladding to hang on the building like the scales on a fish. When it moves, you don't want the scales coming off of the thing. And then the transient drift and the residual drift have to be controlled more so than conventional buildings. For intermediate shaking, you could consider a repairability limit state, but it's not being done today. Ken and others held a workshop on repairability. That's where you plug into this methodology. And then there's the design. And a lot of attention goes into designing these things. Here's a core wall. I'll give you a second to catch your breath. These are big construction workers, by the way. Those are designed and detailed very carefully and inspected pretty carefully, too. Transfer forces are very carefully monitored through the review because most practicing engineers are not really good at understanding how diaphragms work in the US, and maybe not in other places, too. And getting this transfer force taken care of properly is critically important for these buildings. This collector in a tall building in Los Angeles had, if you were to take all the steel in the collector and put it into a square, it would be 0.4 meters by 0.4 meters, grade 400 steel. Okay, so huge forces getting dragged around in these buildings. Design of foundations. I still teach my undergraduates that you make the foundation thick enough so you don't have to put shear reinforcement in it. I tell my engineers that I'm peer reviewing, you put shear reinforcement in there because we know that there's a size effect, that the unit shear strength drops down to about 40% or so of what the strength is from a thin element if you have no shear reinforcement. And so these things are all being built, and they have been for the last 15 years with shear reinforcement. And I'm proud of that one. And then the gravity framing is typically unbonded post-tension construction. And the typical design puts in what we call stud rails. So there's shear reinforcement around all these connections. I remember Professor Park doing tests, not quite on stud rails, but doing tests on slab column connections and looking at shear reinforcement and so on. So it's done routinely in these buildings because even though you don't rely on these for seismic resistance, you can't afford to fix them all. And if you don't do this, those are the elements that we calculate are damaged and cost the most to repair. And then there's design and design review. You need a savvy owner who talks to a building official, and the building official has to permit this kind of a process. The design team has to know how to do it, and I know there's many engineers in New Zealand who would know how to do this. And then you need a review panel that's willing to judge whether or not the engineers are singing a good tune or they're not singing a good tune. Do you know these people in New Zealand? I hope so. Anyway, they're from like America's Got Talent or something. But that's where I sit usually. So here's a model of the Salesforce Tower under one of the earthquake ground motions. And by the way, I have to thank Ron Klemenchik from MKA who provides a lot of this material. But you can see how the higher modes are driving this building initially. And eventually, as the ground settles down, the building settles into a simpler sway mode. It's predominantly first mode. And this is not to scale, although the movement is over 3 meters in a building like this, up at the top. And you really try to avoid having buildings that twist, because if you got somebody up in a tall building and the building's twisting, they're not going to be feeling so well. Performance verification in a typical tower. Here's from the Salesforce building. Here's where we would limit the shear stress. We know we can deliver that much shear strength in these buildings easily, considering the demands for flexural ductility are really low. And they check out pretty well. But these checks are routine as what we do. We check core wall calculated longitudinal strains. Again, I don't really believe them so much, but look, here's 0.003, which I think is a fairly reliable compressive strain capacity without any special confinement. These walls never get close to it. And so it's pretty unusual to drive the walls hard in compression, and that makes me feel good. Tensile strains, usually you get up to yield, but not too far beyond that. This building, look, up at the top, where they have the setback is a problem area. And so the engineers have to put additional confinement up there. And they know that because they're doing this kind of analysis. Hardy Cross's codes wouldn't tell them. They look at the foundation demands by defining mean values in the 2 orthogonal directions, create an envelope, factor those up as required for the force checks, and then check that all the orbits of all their demands really do fall within what they're designing for. And check bearing stresses and so forth. In case there's a geotechnical engineer in the office, in the room, we check those things too. What do we learn from all this? Well, we learned what you in New Zealand have known for a long time, and we read your papers and we know it too. We've never been able to get our building codes to recognize it until this year. That the shear forces that you get in the core walls is much greater than the forces that you calculate from the linear analysis by a factor of 2.5. And we've known it, but until the 2019 ACI code, we were unable to get this in. The design of these tall buildings, I think, pushed the code writers over the edge finally because everybody knew it was an open secret. So that's one of the things that happened. Here's a sampling of buildings projects I've worked on. What kind of storage risks do we typically get? They're typically well within the limits. So in terms of service load behavior, likely to be pretty good. At MCE loading, we're pushing close to the 3% limit on some of these buildings. But again, bear in mind the shear stresses are within limits. The strain demands are pretty low. They're drifting this far because they're so tall. Residual storage drifts, pretty low. Do we believe we can calculate these accurately? No. But again, at least we consistently find the numbers are low and there's reasons for it. The inelastic response demands are pretty low. Wall tensile strains, always low, not worried about fracturing. Compressive strains, there they are, barely need any confining steel, but we put all that steel in anyway, just in case we don't know what we're doing. Wall shears are always right up at that limit, always right there. That's what controls these buildings. Coupling beam rotations. They get close to this limit of 0.06, which is where we start seeing strength degradation in diagonally reinforced beams. And this is what they'll look like, I think, based on lab tests. in this MCE loading, they will be damaged. There'll be cracks to fix up. Will the building have to be replaced? Time will tell. We haven't looked at that. Great subject for Ken working on his repairability topics. Let's see, going the wrong way here. Okay. So this sort of gets me just to a comment about the resilient city. And I've had an interest for over a decade in this resilience topic, and I'm not going to go deep into this today because I don't have the numbers to tell you about. But San Francisco is very interested in being more resilient than it currently is. And there's been talk about a resilient city for some 10 years now. In fact, at a New Zealand earthquake conference in Christchurch, I gave a paper on this in 2009. And there's thoughts, well, where are our buildings in terms of their restoration time, given what we currently have for the inventory of our buildings? Not very good. We're talking about months and months and months to get people back in their homes and in their businesses. And we'd like to get back here, something closer to the left. And that requires us to design new buildings to be, especially these tall towers, to be really resilient. So that on average, when you take the existing inventory and the newer buildings, we'll have something that gives us some places that people can stay and be housed. And if people can stay and be housed in a city, then I think the city's got a chance to survive and recover from the earthquake. And I think that the numbers we're getting from these design procedures and the calculations are suggesting that we're on track with these tall buildings. But you don't know what you don't know, right? I think we all learned that in strong earthquakes. And we're way overdue in California for a strong earthquake. And I wish we'd have that earthquake before we built too many more of these things, but this is the way it goes. I'm always impressed to see one of these buildings go up. I'm an academic, but I really am interested in the practice of engineering and earthquake engineering, and I enjoy seeing a building go up. So let's take a look at what one of these looks like. So we start down at the ground. By the way, those of you who are debating, young students debating going to Stanford versus Berkeley, that's a Stanford engineer. We don't know whether he got out of there or not. But the tower comes up to the transfer level, first floor, so there's the bars coming through. And at this time of this building, lap splices were permitted at this location, but they're heavily confined. The next code, there's going to be restrictions in the US on where those go. And then here's that picture again, in case you didn't get a picture of it with your phones, of that core wall going up. And this is typical of how they look as they go up. And then let's take a look at a building from farther away, and month by month, look at how the construction goes on the typical tall building. So there's a core, starts up, and goes up. And look how tall it's getting. And right about now, it begins to feel like, oh my gosh, let's get the rest of the building up there so that it can support this very slender, skinny tower. It's not how it works. The tower is supporting the rest of the building, right? So this is the building at its best. But it's usual to slip form these towers so that you get one crew working on one thing, and then the other crews start following. So you get multiple crews working on different floors at the same time. So the flooring starts up, the tower's going taller. July, August, September, they're starting to put the cladding up on the outside, the scales on that fish. November, December, January, February, and March, and there it is. So that's how it goes up over the span of a year to a year and a half. The design and review process might take a year. And most engineers promise the owner, oh, it's 6 to 9 months, but sometimes it takes longer because these reviews are done very seriously. These are serious buildings. And I like the idea of these buildings, not because I want to build on everything, everywhere, and have buildings and buildings and buildings, but I think these are centers in our cities where people can live and have fun They don't have to drive from the suburbs or drive back to the suburbs after work. They can stay and live in a good environment close to where the action is and enjoy life and not be stuck in the traffic, some of which I was surprised to see also here in Auckland in the last few days. And here's just some pictures of some of the projects for which I was showing data. Those data points were these various projects. And they're Seattle, San Francisco, Los Angeles, Long Beach, and San Diego is where most of them go. But I've looked at in detail all these buildings and several more. So here I conclude the presentation. This is how it's being done right now in California and up and down the West Coast. Looking at designing tall buildings in a way where we're doing our best to understand the mechanics, doing our best to make sure that the structures that are being built, even though we're calling them risk category 2, they're designed well within the limits. So I think that they'll help us have a resilient community after the next earthquake. But rather than leave you on that very, very positive note, the next earthquake will tell us whether we're actually doing it right. Thank you.